Welcome to Organic Chemistry. In this video, we tackle benzenes and electrophilic aromatic substitution. Let's get started. In situating benzenes in a larger landscape of functional groups, we recognize our ordering. At the top, we have highly polarized pi systems, carboxylic acids, anhydrides, acid chlorides, amides, nitriles. These are dominated by strong carbonyl or linear pi interactions. As we move downward, we lose polarization and resonance stabilization. And by the time we reach aromatic rings, we are dealing with something unique, like we discussed in the last video. A fully conjugated pi system that is resonance stabilized across the entire ring. One of the idealized versions of periodicity, as we saw. So benzene is not just another alkene. Breaking aromaticity is enthalpically expensive. And that single idea explains everything that follows. We return to this slide that we introduced with aromatic systems. Substituents influence benzene, specifically through two channels: inductive effects and resonance effects. Inductive effects refer to electron movement through sigma bonds due to electronegativity. And resonance effects refer to electron donation or withdrawal through pi conjugation. They must always be considered together. Electron donating groups either donate lone pairs through the ring, resonance, or donate through hyperconjugation. Electron withdrawing groups either pull through electronegativity, i.e. induction, or pull through pi conjugation into carbonyls, nitro groups, nitriles, etc. Halogens are the famous exception. They withdraw inductively but donate weakly through resonance. And that tension produces the unusual directing behavior. Now, when electrophilic aromatic substitution occurs, we temporarily break aromaticity. The intermediate is a sigma complex, an rhenium ion, with a delocalized positive charge. So electron donating groups will stabilize this cation at the ortho and para positions by resonance. They therefore increase electron density there. They make formation of the sigma complex easier. Therefore, it will be a faster reaction. Ortho, para will be major. Electron withdrawing groups do the opposite. If substitution occurs ortho or para to the electron withdrawing group, the positive charge sits adjacent to a withdrawing group, and it's highly destabilizing. Meta avoids that destabilization. Therefore, electron withdrawing groups slow the reaction, and the meta position will be major. That is not memorization. That is cation stability. If we treat alkenes with Br2, addition occurs. But if we treat benzene with Br2 alone, nothing useful. Why? Because addition destroys aromaticity. Aromatic stabilization energy is large. Breaking it requires enormous enthalpic compensation. Instead, benzene chooses substitution. Remove a hydrogen, restore aromaticity. So we need a stronger electrophile. Enter halogenation using Lewis acids like aluminum chloride or iron 3 bromide. Lewis acids, like aluminum chloride, polarize the halogen. They generate a much stronger electrophile, effectively Cl plus or Br plus. Now it's the benzene that attacks, and we form the sigma complex. Then we use a base to remove the proton, and aromaticity is restored. 3 key takeaways. Is this regioselective? Most definitely, yes. Rearrangements, however, no, because there's no free carbocation. And is this stereoselective? No. We're in a planar ring system. And notice the similarity between aromatic halogenation and aromatic nitration and aromatic sulfonation. In aromatic nitration, we use nitric acid and sulfuric acid to generate the nitronium ion, NO2, with a positive charge. That is the true electrophile. Sulfonation, however, uses SO3 in sulfuric acid. Both follow the same mechanism. We attack, we form the sigma complex, we deprotonate, and then aromaticity is restored. Nitro groups are strongly withdrawing, and sulfonic acids are also strongly withdrawing. These will dramatically change directing behavior in later reactions. And this leads us to Friedel-Crafts alkylation and Friedel-Crafts acylation. In alkylation, we generate a carbocation using aluminum chloride. But now the danger appears. Real carbocations can rearrange. There's hydride shifts or possible methyl shifts, and we lose control. Polyalkylation also occurs because alkyl groups will activate the ring. This reaction works, but it is most definitely messy and not preferred. However, Friedel-Crafts acylation solves the problem. Instead of a free carbocation, we form an acylium ion. The positive charge is resonance stabilized between carbon and oxygen. Therefore, there is no rearrangement. The product ketone is deactivated, preventing multiple substitutions. Therefore, Friedel-Crafts acylation is cleaner and more controllable. Now, in 1897, we have the Gattermann Koch mechanism discovered. Instead of starting with an acid chloride, we build the acyl electrophile from carbon monoxide. Copper 1 chloride in HCl coordinates to carbon monoxide. This weakens the triple bond. That's enormously strong. Then protonation occurs, and chloride attacks to generate the formal chloride equivalent in situ. It is aluminum chloride that activates it, and again we generate the acylium type species, but this time it's formal, as in just one carbon. It's the same logic as before, resonance stabilized electrophile. The ring attacks, and then we have a loss of a proton, and then we install an aldehyde. The big picture is that Friedel-Crafts acylation installs ketones, whereas Gattermann-Koch reaction mechanism installs aldehydes. Both operate through acylium type electrophiles. There are no rearrangements. Now, when predicting products with multiple substituents, we first prioritize the strongest activator because kinetics will dominate. Then we check if directing effects agree. And finally, we consider sterics. The rhenium ion really is the key intermediate. If we stabilize it, it will be a faster reaction. If we destabilize it, it will be slower. always think of this in terms of sigma complex stability. Now we switch gears. This is not substitution, it is oxidation, and it is brutal. We gesture to our reagents. Potassium permanganate hydroxide heat. This completes the loop on the reagents that we will not actually use in a laboratory setting. Mercury, chromium, manganese. Here is the rule. If there is at least one benzylic hydrogen, permanganate will oxidize that entire side chain to a carboxylic acid. It does not matter how long the chain is. Everything past the benzylic carbon is destroyed. If we look at our mechanism, we see a succession of oxidation and reduction. This all follows along until we get to our carboxylate ion that's formed, and protonation is our final step in which we form the carboxylic acid. Eventually, though, everything ends as manganese 4, and it condenses and it forms these bridges and precipitates out of solution. It is this brown sludge that you would see in a flask. That's your oxidant being consumed. Regioselective? No. If there is a benzylic hydrogen, that's the key. If there is none, no. But if there is, then it is happening. Rearrangements, nope, no fixed carbocation. And stereoselective, no, absolutely no. But this is one of the harshest reagents that we would encounter. It is not substitution chemistry. It is oxidative erasure. We end this video on some reduction chemistry. Reduction chemistry changes the substituent behavior. Metal acid reductions convert nitro groups into amines. That transforms a strong electron withdrawing group into a strong electron donating group. Hydrogenation can reduce alkyl side chains under harsh conditions. Clemmensen reduction reduces carbonyls to alkanes under acidic metal conditions. These transformations let us build a strategy. We can install, we can modify, we can then activate or deactivate. So aromatic chemistry is most definitely like a form of chess. Therefore, aromaticity really is something special. Our reactions can only occur if aromaticity can be restored, and substituents influence where that temporary loss of aromaticity is most tolerable. That is the logic of electrophilic aromatic substitution. Till next time, Crip.